Hi there, welcome to the second video in Fourier Expansions. In this video we're going to run through the exact computations that one would need to do to compute the Fourier expansion that we did in the last video. Okay, so let's take a look. In the last video we looked at the function 1 minus x squared on the interval minus 1 to 1. And what is the formula for the Fourier expansion? It's given as follows. So in order to determine the particulars here, we need to determine the constants a0, an, and bn. L appears in this formula. L is determined by the interval. The interval is an interval from minus L to L, so in this case, L is 1. Okay, so how do I compute those A's and B's? Well, here's the formulas that we had from the last video. But we can make some observations. Since f happens to be an even function, this is an even function, and what does that mean? That means that f of x equals minus x for all x. It is an even function, and therefore bn is equal to 0 for all n. Why is that? Well, if you look at the integral for bn over here, bn involves multiplying our function times sine of this stuff. Well, sine is an odd function. If you multiply an even function times an odd function, you get an odd function. So this is an odd function in the integral. We're integrating from minus L to L. Well, the integral from minus L to L of any odd function at all, will always be 0. That's a calculus 2 trick that is really good to know. If you integrate any odd function from minus L to L, you get 0. So that makes bn 0. Now, the other observation is, since f is an even function, we can express these integrals for the a's a little bit more simply. An even function, when you integrate it from minus L to L, it's exactly equal to what you'd have if you integrated it from 0 to L and then multiplied it by 2. And that's because to the left of 0, it's the same as what it looks like to the right of 0. So you just do 1/2 and multiply it by 2. So that's what I did. I just took these integrals here, and instead of integrating from minus L to L, I integrated from 0 to L and then doubled them. And so that's another way to express the a's in this particular case where we have an even function. And that'll make those integrals a little bit easier to do. Okay? So here we go. Here's our a0. So remember, L is equal to 1 in our case. So that just becomes this. F of x is 1 minus x squared. So pause the video now, compute this out. All right? So you've computed it. Let's check our work. You should have gotten 2/3. Okay, that was pretty straightforward. Now let's do the ANs for n greater than 0. Here's our formula. Remember, L is equal to 1, and f of x is 1 minus x squared. So there we go. Now I'm going to distribute that cosine across that polynomial. All right. Now pause the video, compute this integral. This will take a little bit longer. All right, you got it? Okay, I'm not going to show the steps, but I will show the final result. What you got should have been equivalent to this. Okay? Now, that looks pretty messy, right? That looks pretty ugly, but it really isn't. It's really quite all right. Why is that? Well, first of all, look at that sine n pi. Here's a graph of the sine function. Now, what's special about sine? When you evaluate it at any integer multiple of pi, it's always equal to 0. So bye-bye sine n pi. And what about this? What can we do next? Well, now I've got these n pi's in the numerator and denominator. They're factors, so I can cancel them off. All right, so this whole thing simplifies to this. Not too shabby. Now, what about cosine n pi? Well, let's take a look at that. Well, cosine of n pi is either equal to 1 if n is even, or it's equal to -1 if n is odd. So we can just change cosine n pi to -1 to the n. So there you go. That simplifies pretty nicely, right? All right. moving along. Remember, this is our Fourier expansion. So now let's just substitute in those coefficients that we just derived. There you go. Remember, the b ends are 0, so they're gone. So we get this. If you were to expand it out term by term, we would get this. And that is the Fourier expansion for f of x.